All right, I'm going to go ahead and close the timer. And it seems like I have the stage, so we're just going to go ahead and hop into things. Welcome to my Appleseeds 2021 talk entitled Algorithms as a Tool of Thought. My name is Conor Hoekstra, and I go by code_report online. So if you're trying to find me online on Twitter or YouTube, it's sometimes easier to search for code_report. Otherwise, just Googling my name sometimes works. The first thing I want to say is that the slide deck for the slides that I'm showing right now can be found on my GitHub page. And in a practice version of this run, I got a comment that my code syntax highlighting isn't the best if you're colorblind. The best solution that I found for this is a Chrome extension. For some reason, actually, there's not a lot of PDF colorblind sort of converters. And when it comes to APL syntax highlighting, there's no easy way to sort of have multiple different versions of a talk. So it's not going to be super important, but if it is something that you do struggle with, my recommendation would be to go to the GitHub, click on the slide deck there, and then use the extension. The next slide is an About Me slide. I'm not going to spend too much time on this because I want to get to the APL stuff. But I have a podcast, a YouTube channel, a programming languages meetup that happens virtually. In general, I'm a programming language enthusiast, and APL is by far my favorite language. But most importantly of all this stuff, I work at NVIDIA on a team that works on an open source suite of libraries called Rapids. And I'm a professional C++ engineer on that team. So I don't do any APL in production. I only started learning APL at the tail end of 2019. So I'm barely one APL year old. So similar to Martin, you might consider me an APL baby. But even though I develop in C++ professionally, I absolutely love APL. So you should note that I am on the International Standards Organization for the standards body that works on C++ development and language and library evolution. I primarily focus on algorithms and designing sort of the next generation algorithms in C++. So I sort of within the C++ community, I'm known for my expertise on algorithms, which relates to APL because a lot of that expertise comes from falling in love with APL and other languages like Haskell. So even though I develop in C++ on a day-to-day basis, these are my top 5 favorite languages. So C++ doesn't even come close to number 1. That's not because it's not an amazing, powerful language. I just have a lot more fun programming in APL. APL and Haskell are definitely the top 2 by a long shot. And then this is actually the list of 5 that I gave when I was on a podcast a couple months ago, back in 2020. Racket and Clojure, if you don't recognize those logos, are number 3 and 4, respectively. They're both Lisp dialects, but in 2021 now, I would probably update this and say that Clojure ranks number 3 and that Elixir is tied with Racket now. And something you might note if you include APL as one of these is that all of the top 4 languages are functional programming languages. So C++ is not at all known for functional programming, but we are getting a lot of features like algebraic data types, lambdas, et cetera, in the more recent standards. So we're on C++ 20 now. C++ 23 will be the next standard. So the point to know is that I'm speaking to you not as an APL expert, but just someone who absolutely loves the language. And I tend to spend a lot of time learning different programming languages, which makes me have an interesting perspective when it comes to learning new languages. I'm going to start by talking about the title of my talk, which is Algorithms as a Tool of Thought. So for the experts, APL experts that are watching, you will all know that Ken Iverson, the creator of the language, won a Turing Award in 1979. And his Turing Award lecture was entitled Notation as a Tool of Thought. That's a phrase that you'll hear commonly. I think you've heard it a few times today already from Rich and others. And it's this idea that the symbols in APL are not just a notation for mathematics, a notation for programming, it's a notation for thinking. And for a long time, that being only several months because I've only been studying APL for a bit, I thought that the title of this paper was not the best title. I thought it should have been Algorithms as a Tool of Thought, because all of the symbols in APL I think of as algorithms. All of these here in the green symbol, these are all algorithms, in my opinion. They're referred to as functions by APLers, but I think of them as algorithms. I realized that notation as a tool of thought was the correct title for that paper. And you've heard this earlier from Rodrigo already, is that there's both functions and operators in APL. So the bottom line represents operators in APL that you can combine with functions to get really expressive things in APL. So I think of these as not functions and operators, but algorithms and operators. Like I said, APLers refer to these as functions. And also as a sort of piece of history in J and in Dictionary APL, which was sort of a pure dialect that a paper was written about, they refer to these as verbs and adverbs and conjunctions. But I think of these as algorithms and operators. And the reason I think of the top line as algorithms is because if we take a look at 4 of these, the names of these functions or algorithms are reverse, unique, partition, and iota. And if you compare these to sort of sibling algorithms from C++, their corresponding names are reverse, unique, partition, and iota. Iota specifically comes from APL. There's one other language in Martin's talked quite a bit about Go. Go also has an iota. It does something slightly different. But so these 4 algorithms on the right come from 2 different headers in C++. One of the first 3 are from the algorithm header, and the second one, or the iota, is from the numeric header, which is basically considered just another algorithm header. So even though these are referred to as functions in APL, I think of them as algorithms because in my day-to-day programming in C++, these are algorithms that we reach for. So note that there's sort of, I might use the word algorithm, even though it's probably more accurate or more APL speak to say functions or symbols. But I think of these as algorithms. And in today's talk, we are going to focus on specifically building up one algorithm. And that algorithm is all equal. So this is an algorithm that I find super, super useful. And it comes up quite often, especially in writing like unit tests and in writing sort of asserts in your code. But it's an algorithm that I've only been able to find in sort of first-class libraries of 2 different languages. The first one is Haskell. And you don't need to really be able to read Haskell. It's a pretty straightforward syntax. Here, we're just making 2 calls to all equal, and we're passing it a single list. So all equal takes a single argument, which is a list of numbers or a list of objects. And it's just going to check, are they all equal to each other? So in the first example, we have 1, 2, 3, 4. Clearly, those are not all equal to each other, so it's false. And in the second example, we have 1, 1, 1, 1. So these are all equal to each other, so it's true. And the other language that I have found all equal in is Python. So looks very, very similar, even though they're very different languages. The only difference really here is that we're using a snake case instead of Pascal case, and that we're using a set of parentheses to pass our argument to our function. And the comment is a hash or an octothorpe instead of a double dash. And this is designed to be an extremely simple algorithm. You could do something more fancy, but the idea of this talk is to show you several different ways to solve or program this algorithm in APL to show how easy it is to combine different operators and different algorithms or functions and build up beautiful expressions in APL with only 3 to 6 characters. And you can do it. We're going to look at 5 different ways in detail, but there's going to be 8 in total at the end of the talk. And I'm probably going to release a supplementary YouTube video that walks through these, not in a slide deck, but similar to what Rodrigo did with the actual RIDE editor and building up these expressions one by one. So one extra comment is that technically JavaScript, I did find a library that has an all equal, but it's not like a first-class library. And you could make the argument that Clojure and Racket don't need to implement this because it's just an apply equals in those languages or any list for that matter. But yeah, just thought I would highlight this. So let's jump into solution number 1. This is our first solution. So this is actually a great follow-on to Rodrigo's talk. So if you're watching my talk right now on YouTube, I would highly recommend pausing this, going back and watching Rodrigo's talk, because Rodrigo walked through in a little bit more detail than I'm going to in some of these solutions. So this is a great follow-on to Rodrigo's talk. But visually or verbally, what this piece of code on the screen is doing is it's checking whether every single element in your list is equal to the first element. And note that in the top right-hand corner, you have a little point-free Unicode emojis. Anytime you see this on the screen, it's because you're looking at a point-free solution, which means that in order to run this, you might need to either assign it to a function or put it in parentheses in order to pass an argument to it. Any other time you see code on the slide, you can probably just copy and paste it into an editor or to tryapl.org and it'll work. Yeah, just look out for the point-free on your slide deck or on the screen for when you're looking at a point-free solution. But let's start to walk through this first solution. So the first thing we're going to look at is first, pun intended. So this algorithm or function, which looks like a horseshoe, is first. And what it does is, given a list of numbers, it just returns you the first one. Pretty straightforward. So that's all I'm going to say about first, because I don't think anything else needs to be said. Now what we want to do is check if this first element is equal to every other element in the list. And we can do this using what is in APL called a defun, that's represented by the braces. But in any other language is basically called a lambda or an anonymous function, or if you're a small talker, a block. There's several different names for this, but basically it's just a function without a name. And inside it, what we're doing is we're using our first algorithm and applying it to omega, where omega is basically your argument. So in other languages, you name your arguments. So in Python, you might see lambda x and then colon x equals 1. Here, we don't name x. Omega is always your argument. And we're only going to look at code that deals with one argument. You can have defuns that have 2 arguments, but for the purposes of this talk today, we're just going to be dealing with defuns that have 1 argument. So here we're applying 1, 2, 3, 4 as our list. And then inside the defun, we're checking whether the first element is equal to our list. And so if we substitute this, it looks like following. And once again, if we apply our first, we end up with this. So 1 is equal to 1, 2, 3, 4. And I'm not going to go into detail on why this works, but it's basically a very 2 fancy words called rank polymorphism, where when you have a scalar and a vector, or a vector and a vector, or a matrix and a scalar, these all work. So basically, this is going to check on an element by element basis. Are these values equal to 1? And in APL, as we saw in Rodrigo's talk, 1 is equal to true and 0 is equal to false. So because we only have one value that's equal to our left-hand value 1, we're going to get 1, 0, 0, 0. And once we have this set of Boolean values, we just need to do basically a logical AND reduction. And this is sort of a repeat from what Rodrigo said earlier. This is basically just putting the logical AND in between each of these values. This is known as a fold or a reduction in many other languages. This is sort of another sort of Google Translate of all the different languages. So you can see predominantly this is called reduce in many languages. Some languages call it fold. Note that it says fold L on for Haskell and Racket. Technically, APL's fold or reduce is a reduce right or a fold right. And that actually was asked earlier in the chat. But yeah, so just good to note that this is basically a reduction. And fun piece of trivia is that reduce actually comes from APL. And a lot of people think it's because we're reducing a single or a list of values down into a single value. But the reason reduce is called reduce is actually because when you have an n rank array, so if you have a matrix, which is rank 2, and you do a reduction on that, you're reducing the number of dimensions by 1, which when I discovered that, I thought was super awesome. Even though I think a lot of people think reduce is sort of you're reducing a list of values down into 1, it's actually because you're reducing the number of dimensions. Anyways, hopping back to our code here, if we perform this reduction on our 1s and 0s, we're going to end up with 0 because we don't have all 1s. And that's basically it. So you'll note that this is the code that we have at this point when you combine the reduction with our defun. And this is not the code that I originally showed. This is a little bit more verbose. And this is because we're making use of something called a fork, which is something that I'm also not going to go into a ton of detail about. But basically, whenever you can build up this pattern where you have 2 functions that take a single argument, aka monadic functions or unary functions, and then a binary function in between, which is our equal. So equal takes 2 arguments, you have what's called a fork. So here, the 2 monadic functions are first and wait, where's the other monadic function? Well, technically, we can modify this slightly to just pass it same, which is the APL equivalent of identity, which is a function that just returns you what you passed in, which a lot of times seems useless. But in this case, it's exactly what we want. we want first and same as our monadic functions, and then equal as our binary function. And so what happens is omega is first passed to, first and same, and then the results of those two operations are passed to the binary function equals. And whenever you have this, you can drop all the braces, all the parentheses, and all the omegas and be left with this, which is one of the reasons I love APL so much, because you can just build up these super beautiful expressions. So if we sort of highlight the names of these, the horseshoe is first, the equal is equal, the hat is logical and, the right tack is same or identity, and the slash is reduce for the reduction operator. So let's move along to our second solution, our solution number 2. And this is what this one looks like. So verbally, what this solution is doing is it's taking the unique elements from our list of elements and then checking whether the number of elements in that unique set is equal to 1. Because if you only have a single unique element, that means that all of the elements have to be equal. So once again, let's walk through this step by step. This is our U, which stands for unique in the monadic case. And when you give it a list of numbers, note I've slightly changed our input so that it gives a little bit of a better visualization of what's happening here. When we call unique on 1, 2, 2, 4, it's going to remove the duplicates. So you just end up with 1, 2, 4. And from here, what we want to do is take the size of this list or set. And in order to do that, we're going to call an algorithm called tally, which seems like a bad name, but it's actually a brilliant name when you realize that if you rotate the tally symbol 90 degrees, you end up with what looks like basically keeping score on a chalkboard. So you're tallying up the number of elements in this list. Obviously, the length of the tally of this list is 3. And then from here, all we want to do is check, is this equal to 1? And if it is, you have unique elements. So obviously this is not true. So we're going to end up with 0. And to recap, putting that all together, we've got 1 equal to tally unique of our input. And in order to make this point free, we just have to do the following. So yeah, this is another really beautiful solution in my opinion. And to me, these two solutions were the two most obvious in terms of how to solve all equal, or how to write all equal. Once again, sort of delineating what these are called. The U is for unique. We already saw equal for equal. And then the tally is the sort of 3 horizontal lines with a slash through it. Let's move on to, oh, right. So this, you might have been thinking that this is actually incorrect, because what if you have an empty list? So we just have to make one small modification, and that's with replacing the equal sign with a greater than or equal to, which is, it's just so beautiful in my opinion, because in every other programming language, other than maybe Julia and a couple others that allow Unicode symbols, this is going to be 2 characters. But here it's completely symmetric. You just do a single symbol replacement, and absolutely beautiful. So this is greater than or equal to. On to solution number 3. So if you've been playing along in your head thinking, how many different ways are there to solve this? This is where they start to get a little bit less intuitive, or less obvious, like they don't jump to your mind right away. And this is maybe not my favorite solution, but it contains one of my favorite things from APL when I discovered it. So verbally, what this solution is doing is it's checking whether every 2 adjacent elements are equal to each other. So it's basically taking 2 elements at a time that overlap and checking, are they equal to each other? And if every single pair of adjacent elements are equal, you know that by definition, they all have to be equal. There's some proof in there that I'm not going to show, but you can sort of just reason about it and it makes sense. So let's see this via example. Once again, sort of changing the input so you get a nicer visualization. Here we have a 2 equals reduce, and then with the input 1, 2, 3, 3. So this is an equals reduction, but it's specifically combined with a number on the left, which makes it an n-wise reduction, where n can be any number. Here, n is 2, but it could be 3, it could be 4. And basically what this is going to do, and the best way to visualize this is to actually first replace the equal sign with a comma, which is catenate, which means it's going to create, it's going to catenate the pairs of elements. And so if we do 2 comma reduce 1, 2, 3, 3, we're going to end up with a nested list of sort of sublists where each list is the adjacent elements to each other. So the first sublist is 1, 2, the second sublist is 2, 3, and the third sublist is 3, 3. And so once again, this is what 2 comma slash 1, 2, 3, 3. And if we replace this comma with a binary equals, that's basically going to insert equals in between each of these pairs of elements. And then when we evaluate this, we're going to end up with 0, 0, and 1. And what's absolutely amazing about this is that you can replace that binary operation with any operation that you want. So here we have equals, but we can just as easily replace this with plus, and now we have an n-wise plus reduction. And once you evaluate this, you're going to end up with 3, 5, and 6. And I think this is actually this is absolutely brilliant, because for the first like half year when I knew of this n-wise reduce, I didn't realize you could replace the comma operator, and I was still using it all the time. And basically just doing like mapping over the nested list with some kind of reduction. And the day that I realized you could replace the comma with any binary operation, my head basically exploded. And what's even cooler about this is that this dates back to APL in, the 60s and 70s. But this is actually a very, very common algorithm that shows up in data science libraries like Rapids QDF, the library that I work on day to day. So QDF specifically is a data frame library that's GPU accelerated. It's a part of the Rapids open source suite of libraries I mentioned at the beginning. It's based on Pandas, which is basically a Python library that runs on the CPU. So QDF is basically just a GPU accelerated version of Pandas. But both of these, including the C++ backend, have algorithms called rolling, which is exactly an n-wise reduction. It's basically taking sliding windows and then on each of those sliding windows applying a reduction. So even though APL was invented, half a century ago, it is still having an impact, not just on the names of the algorithms like reduce and scan, but also on like actual day-to-day algorithms that are being implemented in libraries like that I get paid to do. So this is super cool. Coming back, so we have our n-wise reduction with equals. This is going to give you 0, 0, 1. And then as we saw before in our first solution, once we have these Booleans, we just basically want to do a logical AND reduction. And if they're all equal to 1, you'll get 1. Otherwise, you're going to get 0, which in this case, you'll get 0. So super awesome. N-wise reductions are super, super cool. And once you sort of wrap your head around them, you start to use them all over the place. So once again, here are our symbols, and you'll note at this point that we actually did not introduce anything new here. We've seen and, we've seen equal, we've seen same, and we've seen reduce. The only thing that we introduced here was the n-wise reduction. So already we're at the third solution, and we're just reusing symbols, algorithms, functions that we've seen so far, which is, I'm trying to highlight like how quickly we're already using what we've learned, and we've only learned a fraction of the symbols in APL. So moving on to solution number 4, which is the second last one that we're going to look at in detail. And this one, I think the chat's turned off. Feel free to turn the chat on. I forgot to mention that at the beginning, Rich. And +1 in the chat if it ends up getting turned on, if you thought of this solution, because this one's pretty tricky. So this is, once again, a fork. So it's got 2 monadic operations on the left and right, and then a binary operation in the middle. And this is basically checking whether the minimum element is equal to the maximum element, which I think is just fantastic. So if we take a look, this is once again where we have the reduce operator, and we're combining it with the minimum binary operation. So far we've seen logical and we've seen an equals reduction in the n-wise reduce case. So this is our third reduction that we're seeing, which is minimum. So it's the minimum glyph combined with the reduce operator, or sorry. Oh, this is a bug because I switched it around. So this should actually show 1, not 4. My bad. And then this is going to be the exact opposite. So if we switch this to max, now we should be seeing 4, but we're seeing 1. So in trying to fix my animations, I introduced a bug to these slides. So this should show 4, not 1. So the max is the one with the hat at the top, and the min is the one with the tail at the bottom. And if we show this in the defund version, once again, we're sort of applying minimum on the left, maximum on the right, and equal in the middle. And if you add a set of parentheses, you might be able to recognize the pattern that we saw in our first solution, where we have 2 monadic functions on the left and right, and then a binary function or a dyadic function in the middle. And once again, every single time we're able to build this pattern up, we can get rid of the braces, the parentheses, and the omegas, and just have this, which I just think is extremely beautiful. This used to be our shortest solution, tied with the first one for 5 characters, but we're actually going to see a 3-character solution at the tail end here. So this, to once again delineate the names, here they're labeled correctly. We have min, max, equal, and then the reduce operator once again. And if we, at this point, take a look at all of the operators and functions that we've seen so far, this is the entire list of them. So you can see that like really quickly, with 4 solutions, we only have sort of a limited set of algorithms and operators that we need in order to encode 4 entirely different solutions. So I think I said this is the second last one. This is actually the second last one, number 5 and number 6. Although we're going to go through these ones a bit more quickly because we got 5 minutes left, and I definitely want to leave a ton of time for questions. Solution number 5. Odds are, unless if you're an APL pro, you won't have thought of this one. So this one is very, very similar to our second solution, where we're taking the unique elements from our list of elements and then checking whether it's greater than or equal to 1, or sorry, less than or equal to 1, the size. And here what we're basically doing is we're making use of an extremely useful operator called key, which is the box with 2 lines through it. So this is an example of how key is used. In the most basic case, you pass it a defun that just puts alpha and omega next to each other. So alpha is the other argument. So in a case where you have a defun with 2 arguments, it's not just omega, it's alpha and omega. Alpha for the one on the left because it's at the beginning of the Greek alphabet, and omega for the one on the right because it's the end of the Greek alphabet. And for the input 788 and 999, this is going to give us basically a table of all of the unique values in the first column, and then all of the indices which these values show up at in the second column. So 7 shows up at index 1, 8 shows up at indices 2 and 3, and 9 shows up at indices 4, 5, and 6. So hopefully this is, it looks confusing on the first line, but hopefully with this visualization, it shows you what we actually want. So if we drop the omega and just include the alpha, we're just going to get back the first column in the form of a vector, which is going to be 7, 8, and 9, which sure enough is the exact same thing as the unique values that we got from our unique algorithm that we saw in solution number 2. So we can replace the alpha, because we're not doing anything here, with left tack, which in the dyadic case, basically given 2 arguments, one on the left, one on the right, it just takes the one on the left, which is alpha in this case. And then all we need to do is combine it with the same expression that we saw in solution number 2 with is 1 greater than or equal to the size. And in this case, because 7, 8, and 9 are all different numbers, we're going to get back 0. So this one might have been a little bit too fast, but like I said, we're going through these a little bit quicker just because they're solution number 5 and 6. And Roger Hui in the chat with the 3-character solution, which we're going to get to in a sec. And solution number 6, this one was actually provided to us by Aaron, who you've now heard in the chat if you've been following along, and also Martin gave a shout out with all the tree talks and the code defons compiler. Aaron provided us with this solution, which this is a fork once again. And it's basically the 3 inner characters are an inner product. And then the character on the left is first. And then the character on the right is our identity. So this is actually just a different way to spell our first solution. It's not the same thing algorithmically, but it is sort of semantically, or at a certain level semantically, it's the same thing. Although, algorithmically, the execution is completely different. So if we put this in parentheses and give it 1, 2, 3, this is the equivalent of the following. So we're passing 1, 2, 3 to the 2 monadic operations on the left and right. So first on the left and same on the right. If we evaluate same, it just gives us back 1, 2, 3. And if we evaluate first, it gives us back 1. And so now we have one inner product with a logical and an equal. So what does this do? We've got 2 binary operations here. The first one that's going to be evaluated is the one on the right, the equal sign. So basically, it's going to do an element by element comparison. Is the 1 equal to the 1, 2, and 3? And so obviously only the first element is. And so once we've done this, then we get to our logical and then that's going to perform a reduction. So here, logical and on 1, 0, 0 is just going to give us 0. So like I said, this is very, very similar to our first solution. It's just a different way of expressing it. And with a minute left, that brings us to our final list of solutions. And note that there are number 7 and number 8. I wanted to squeeze them in, but we definitely don't have enough time to go through them. Roger Hui, who is the co-implementer or primary implementer of the J programming language, in the chat basically called out number 7, which what it's doing is you can think of the sort of triangles up and down as sorts. They're not actual sorts, though. They just provide you the list of indices of what would be a sorted list. So if you check whether the sorted indices of your list are equal when you do basically a reverse sort and a normal sort, if those are the same, the only condition that returns true for is that if all the elements are the same value. And that was previously, before Roger said it in the chat, provided by Adam. And then last but not least, Bob, who is a J programmer, pointed this one out, which is, I have a very soft place in my heart for this, because this is basically checking, similar to what we did in the expression above, whether a one rotate is the same thing as your original list. And if you are a C++ developer and have watched any of my other talks, you know that rotate is one of the best algorithms out there, and awesome to see rotate used to solve this solution. And yeah, one last thing, even though I think I'm at time, that I wanted to add, because it's just so awesome. It's super fun building up these expressions. It's like being in an APL REPL and just building up these expressions. It's so much fun. But also, like, profiling in APL is so much easier than like any other language, except for maybe Python has this sort of little time functionality. But in APL, you can use the bracket runtime -c, or you can use CMPX, which is typically what I use. So if you just use CMPX and you pass it a number of different expressions, you saw this earlier once again in Rodrigo's talk, it gives you this nice little diagram and shows you a comparative analysis. And you can see here number 7, because we're basically doing 2 different sorts. This one is infinitely worse than all the other ones. So if we basically normalize and get rid of the runtime of number 7, you end up with this really cool sort of profiling of our different solutions. So you can see that by far the fastest is the inner product. So even though the inner product in solution 6 is basically doing the same thing that solution 1 is doing, because of optimizations and vectorization and a bunch of fancy stuff that happens behind the scenes in the Dyalog APL implementation, you get a 2x speed up compared to solution number 1. And I just find this kind of stuff is super cool. So to recap, after our first 4 solutions, these are the number of operators and functions that we were looking at. After all 6, excluding the last 2, this is the full list. And these are your algorithms as a tool of thought. Having these be single symbols doesn't seem like a big deal, but when it's so easy to build up these small expressions and play around with different ways to implement this stuff, it changes the way that you think about algorithms. In C++, when you want to spell out an algorithm, it's 10, 20 characters. You include the iterators and the lambdas and all the syntax. You can still get things done, and it's extremely performant, but it's a lot harder to fit that model in your head. The APL model fits so easily in your head, and it's basically like being in an APL REPL is like sitting in a playground of algorithms where you just get to throw things around, and it's so fun. And I can't recommend highly enough that those of you that are APL curious, even if you don't ever plan on writing a line of production code in APL, you go and try it out. How do you do that? I'm sure links will be provided all over the place, but try APL is the easiest way to get started. It's the equivalent of Compiler Explorer in C++ Topia. You just go to tryapl.org, you start typing. If you don't know the shortcuts, you can just click on the symbols above. It's really easy to pick up. If you want to invest a little bit more, I highly recommend the RIDE editor. You can download Dyalog at Dyalog APL and then get the RIDE editor from the GitHub Dyalog site. I have not committed this theme, which is the Dracula theme, but I'm going to open a PR so that it looks super nice. And yeah, I found that RIDE is like by far the best experience in terms of learning APL. That's all I have to say. Thank you so much for listening, and I'm happy to take any questions that folks have at this point.
Yeah, the rest of thanks for that, Connor. Yeah, the rest of the time's yours till 5. So there's a little bit of stuff in the chat, and there seem to be 3 questions in the Q&A. So feel free to address those. And
sure,
such.
Yeah.
Oh, and if you address those things, please read them out. But
yeah, I definitely will. So the first one was actually, I think, asked before the talk started. So a question for Connor. As he's very knowledgeable about numerous programming language, would it be possible for him to share some thoughts regarding APL and J? And I'm not sure, but I got this exact question on a YouTube video yesterday, and I hadn't responded to it. So potentially this is the same person. So I don't know. I'm in the midst of learning J, and my knowledge of APL, I'm not sure what the coefficient of it is in terms of the multiplier, but I know more about APL than I know about J. What I would say about J is that I am super interested in learning it because it was Ken Iverson's second project. Some people, like, I refer to J as the daughter language of APL, and some people, when they hear me say that, they say, no, like J is APL. It's just the evolved version. It's not like a daughter language. It is APL. It's just spelt differently. And so my thought is that all of Ken's best ideas, like there's a superset of his ideas in J when compared to APL. And a lot of the features actually that are in Dyalog APL have been folded back into APL from J. So my interest in J is that I want to learn like all of Ken Iverson's genius, because I think he's probably one of the less well-known, like he should be as famous as like every other computer scientist that we know today. And like many of the APL folks in this chat will have heard this mini story, but I'll tell it super quickly. The short version is that Bill Gates showed up in the early 80s at a company in Toronto, IP Sharp and Associates, and he was exploring, ideas because he was in the midst of building the PC or getting ready to build the PC. And he ended up putting BASIC on the PC. But there is like a parallel universe where his visit to IP Sharp went slightly differently, and he ended up putting APL on the PC instead of BASIC. And the world we live in today as computer scientists or software engineers would look immensely different, because a lot of the languages we write today look like C and look like BASIC and Fortran. But potentially there's a parallel universe where every language that we write today looks more like APL. Anyway, so I want to learn everything that was in Ken's head. And I think the best way to do that is by learning J. That being said, right now I'm more in love with the APL symbols. Like there's so much meaning in all of the Unicode symbols to be discovered. Like anytime you think, oh, that's a bad symbol, you haven't understood it. Like I thought tally was a really, really bad name for a very long time, because every other language I know either calls it size, length, or count. And then I show up to APL and they've decided to do something novel, except it wasn't novel because they were like the third programming language ever invented. But it just seems like, why did they choose something that seems non-obvious? And then you realize, oh, it's because they're trying to capture the meaning of like it's rotated 90 degrees of keeping score on a chalkboard. But yeah, I think they're both extremely incredible languages worth learning. And whether or not, I haven't made up my mind if one is better than the other. I think APL has the Unicode characters, and I think J has like the superset of ideas. Also 13 : enables you in J to convert non-point free or tacit solutions into point free or tacit solutions. So point free or tacit, if you're not familiar, just means solutions without arguments that don't mention like omega or alpha. And in APL, we don't have the ability to convert those. And it's amazing in J that you can go between those. So I'm not sure if Roger, if you implemented that, but like when I discovered that, that's the singly most amazing thing that I found in J so far. That was way too long of an answer. So yeah, Bob pointed out, oh, right. So I think the not quite, because on the min-max solution, it's only going to work for, is that actually?
Just numbers, I think.
Yeah. So yeah, there are a bunch of small footnotes that I did not mention. Certain solutions have cases that they don't work for. But for the purpose of this talk, I wanted to like avoid mentioning all the sort of, oh, and also this and also this. But yes, that's a good point. Scott says, excellent presentation. Thank you. When you gain experience with APL, do you begin to recognize small patterns like these units, like English words? Yes, 1000%. Literally, in my meetup 2 nights ago, we ended up watching the most recent YouTube video that I'd made that was solving a small LeetCode problem. For the purposes of this answer, it doesn't matter. And a question that I got was, it makes sense when you watch people build these expressions up, but do APLers are they actually able to read it without like an immense amount of difficulty? And the answer to that question is yes. You could say the same thing about Chinese. Like Chinese characters seem impenetrable from like a North American point of view. But like when someone who reads Chinese is reading the Chinese newspaper, they're not struggling to make sense of the sentence structure and the meaning of the text. It's the same thing with APL. When APLers see a set of parentheses with like 3 things inside of it, they immediately recognize that as a fork. And I'm already starting to recognize like certain 3-character sequences, not as like the individual symbols, but like, oh, immediately I know that that's like a certain idiom. And I think it takes time, but like, when we read English, we don't read like Tally. We just see the word tally and we can read it somehow without step by step going through each character. How does that happen? I think just with like years and years of experience. And the uphill battle, one of the uphill battles that APL has is that every other programming language out there looks the same, which then sort of begs the question, well, why would I just go learn this one language when it looks so much different than any other language? And my answer to that would be, well, you're going to think like there's like 1 or 2 orders of magnitude in your ability to like think about problems differently and solve problems differently. Like when I went from C++ to Haskell, it was like an order of magnitude. And then when I went from Haskell to APL, it was another order of magnitude on top of that, or like the jump, even though like I would say it was even more than an order of magnitude. Like my mind was just absolutely blown. And like continues to be blown on a daily basis. Like the @ symbol, I know that exists in APL, but I saw it in Rodrigo's talk for the first time, and like I just learned that. And like every day every day that I am working on APL, I'm learning something. Like the other day, I haven't made this YouTube video yet, but I released a YouTube video a couple months ago that ended up getting like 50,000 views, where I show an APL solution and say it's the best. I was reading a 1979 paper by Ken Iverson, where he has a solution to the same problem in half as many characters as I did. And it was a solution to like a leak code problem, which like I just think is hilarious, because it basically says Ken Iverson was leak coding like 4 or 5 decades before it was even a thing, and he was doing it better than the people that are doing it today. So yeah, APL is just it's even, like I said, even if you're never going to write any APL, I think the journey of like learning it's just going to change the way you think about problems. There's a great talk by Dave Thomas from one of the YAO conferences, where he talks about how APLers are sometimes termed like shape thinkers. They don't think in terms of like programming things serially. They think about programming things in shapes, and like you start with a vector and then you use an outer product to blow that up into a matrix, and then you do something else that blows that up into an n-dimensional matrix, and then you collapse everything down into a single value. And it's hard to like visualize what that means before you start to do it, but like once you're able to use an outer product and then a reduction on that matrix, and then another reduction to a single value, and like in total you have 6 characters that in any other language would take like 10 lines of code, it starts to click. And yeah, once again, I think that answer was way too long, but I apologize.
Don't worry, sounds good. Wait, that was that. I don't know if you want to read the chat. I saw Martin's comment about something old again. Book pamphlet full of idioms. I just wanted to point out, I think it was Veli-Matti Antonen gave me this at an APL conference, and this is a booklet that is a FinAPL idiom library. I don't know when was this? 1984. This was published, and it's pretty neat. I can't read any of the Finnish, but I was able to spot, what's this one? I don't know if anyone will be able to read. I don't know if it'll focus on there or if I got too much shadows. Anyway, I was able to find one, and I recognized it for finding prime numbers. So that was quite fun. But yeah, I think the legacy goes back.
You can find that PDF online, I think. And there's a bunch of like APL idiom booklets that come in like super useful, like in the dialogue competitions. Like I think one of the level 1 questions last year was basically like verbatim from the APL idiom list PDF. Like it was a number 4, number 5. And yeah, it's APL is awesome. Honestly, I've been so I meant to say this at the beginning, but I've been public speaking now for just under 2 years, and I've given like 19 or 20 talks. I think this is number 19 or number 20, and this is my first APL talk. And since December 2019, all I've wanted to do is like talk about APL. And so now this is the first time that I'm doing it. And you can basically go to every single talk I've given in the past year and find some unnecessary reference to APL. About me being like, oh yeah, APL has this, because secretly I didn't want to be on stage talking about C++. I wanted to be talking about APL. But anyways, I'll yield my time because I think we're
That's how they get you. Yes. Thank you very much, Conor. That was really cool.